Hello, today we're going over AP Statistics Chapter 5. We're discussing probability and probability basics. So let's get started right away. The probability of a given outcome is the proportion of times the outcome will occur with a very, very large number of repetitions. Let's boil that down to layman's terms. It's the chance that something happens. So, for example, if I roll a fair six-sided die, the probability that I roll a 2 is going to be 1 out of 6. If I flip a coin, the probability that I get heads is 1 out of 2. It's 50%, 1/2, whatever. Um, where that comes from is that if I do like an infinite number of repetitions of rolling a die, I am going to roll a 2 about 1 in every 6 repetitions. And if I flip a coin an infinite number of times, about 1 in every 2 repetitions is going to give me a heads. So that's where that comes from. Um, that is called a theoretical probability. Experimental probability is slightly different. It's the probability that you get in actual experimentation, because you can't flip a coin an infinite number of times. That's not how that works. But if you were to flip a coin 100 times and you get heads 43 times and tails 57 times, that 43 out of 100 is the experimental probability. It's not the same as the 50% theoretical probability, but that's the probability that was gained in the experiment. So that's where experimental probability comes from. Now, probability follows a number of different rules. We can display these rules with charts and graphs. Let's go over one of these rules before we forget. You can't have a probability of more than 1, and you can't have a probability of less than 0. It either doesn't happen, has some chance to happen, or it always happens. For example, the probability that I am cool is 1. It's 100%, because I'm chill like that. So, let's talk about sample space. This is a sample space of 2 consecutive dice rolls. You have, just to make it simpler, we have a blue dice and we have an orange dice. If you roll the blue die and then an orange dice, uh, the probability for any um, any one of these specific series of outcomes is going to be 1 in 36. You see, the probability of rolling a 1 on the blue and then a 1 on the orange is 1 in 36. The probability of rolling a 5 on the blue and a 3 on the orange is 1 in 36. All of these outcomes have an equal chance of occurring, and together they make up all of the possible outcomes. 36 out of 36, 100% of the outcomes. So let's define events. This is basically just going over the notation for basic probability. Events are typically labeled with just a single letter just to make it easier to rate. So, A or B or C, etc. And the probability of that event is P of A or P of B or P of C. So now, the probability of anything other than that event is P event complement, which is equal to 1 minus P of event. Now, just talking about that real quick, um, the probability that I roll a 2 is 1 out of 6, and the probability that I don't roll a 2 is the probability of 2 complement, which is 5 out of 6. So that's basically how that works. And the probability of either of 2 events occurring is P, A, or B, which is written with this little u, and the probability of 2 events occurring simultaneously is P, A, and B, which is written with this upside down u. So, some relevant formulas that might be good to know is that the probability of 2 events occurring is probability of A times the probability of B when A and B are independent. If they're not, that's going to make this calculation unreliable because these events affect each other. So one happening is going to change the probability of the next one happening, which is going to mess up this calculation. The probability of A or B is a little bit trickier. It's the probability of A plus the probability of B minus the probability of A and B. I'm going to show how this works a little bit by virtue of a Venn diagram. So we'll go over that soon, but just for now, know that subtracting probability of A and B avoids double counting, which is why you have to do that. And now, mutual exclusivity is when 2 events can't happen at the same time, which means that regardless of whatever calculations you do up here, this is going to be 0. So, the probability that it's night outside and the probability that it's day outside are mutually exclusive, meaning that the probability that it's night and day is zero, because that's not how that works. So, these formulas, again, these formulas are useful, but I feel like diagrams and charts are much more effective at describing and displaying these relationships between a number of events. So, let's talk about this probability A and B real quick. I think this is going to be easy to explain with a Venn diagram. So, the part here is A, this red part. The part here is B. You can see that the probability of A and the probability of B occupy the same space. So if you were to add this and you were to add this, these two are going to be on top of each other, which means you're going to have to subtract one of these in order to make sure that you don't count this area twice, which is how this formula works. So right here you can see this part is A and B, and this part is A or B. You know, you have to subtract one of these middle regions so that you don't end up counting that twice, and that's going to mess up your math if you do that. Now, tree diagrams, you can see this looks like a tree. This is like when you have two consecutive events that you're testing. So you have the first event, and then either of these can happen in the second event after this one has occurred. Either of these can happen after this one has occurred. So you end up getting a number of different results. And if you end up adding all of these together, all of these final probabilities, you're going to see that all of these are going to add up to 1. So these, again, this set of 4 dots is essentially your entire sample space. So two-way tables are a specific type of table for probability distributions. And so we can see here, we're talking about gender and weight. So we have totals for each row and each column, and we have 1,200 total individuals. 855 about right, 235 overweight, and 110 underweight. So this is again kind of like comparing two separate events. You have probability of your gender being something, the probability of your weight class being something. So, and then they're all going to add up to the total. Let's talk a little bit about conditional probability. Conditional probability is a special type of probability where you're looking at the probability that something happens given that you already know something has happened before. So effectively what this does is it reduces your sample space so that you don't have to compare as much stuff. Now, I'll show you what I mean by that. Let's talk about the formula for this real quick. This isn't really that big of a useful formula because it's way easier to see what I mean when I do this on a two-way table. But this is the probability of A and B divided by the probability of B. That's going to give you probability of A given B. So the probability that it's 95 degrees outside, given that it's not raining, is 0.25. How that works is that, you already know this happened, this no rain here. And because of that, you can see that it's a 0.25% chance after that it is 95 degrees Fahrenheit. So that's where that comes from. Let's do this again. Probability that it's 75 degrees outside, given that it is raining, is 0.35. You see, you already know that it's raining. Therefore, the probability that it's 75 degrees Fahrenheit outside is 0.35. You can see that right there. Now let's do a little bit of a harder one. What's the probability that it's raining, given that it's 75 degrees Fahrenheit outside? So look at the probability that it's 75 degrees Fahrenheit outside, given that it is raining, and you compare that to the probability 75 degrees outside, regardless of what weather it is. So 0.098, the probability that it's 75 degrees and it's raining, which is over here, out of all of the times that it's 75 degrees Fahrenheit. So which is 0.476. So we can also see this with a two-way table. So let's see. What's the probability that you are male given that you like baseball? Well, we can just take a look at all the people who like baseball because we know that already happened, and we see what's the probability that they're male. So it looks like it's 13 out of 36 because out of the 36 people who like baseball, 13 of them are male. So that's 0.361. Let's do this again. Probability that you like basketball given that you are a female. We take a look at all of the females, which is 52, and we see how many of them like basketball, which is 16. So 16 out of 52 is 0.308. So two events A and B are generally independent if the probability of A is equal to the probability of A given B. Basically, what that means is that the probability for A to occur when B has already occurred is no different than if A were to already occur, which means that the fact that B happened does not affect the probability for A to occur.